Welcome to today's webinar. The topic today is seismic analysis according to Eurocode 8 in RFEM 6 and RSTAB 9. We will present the webinar in RFEM 6. The same workflow is valid for RSTAB 9 for the seismic analysis. But in RFEM 6 are also surfaces possible, and that's not the case in RSTAB 9. Also, the add-on building model is not available in RSTAB 9. But for the seismic analysis, as I already mentioned, it's the same workflow. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the technical contents or content of the website, the German and English webinars, customer projects, newsletters, and so on. I will be the moderator today, and I will answer your questions. The presenter will be Thomas Eichner. He's responsible for product engineering and customer support. And for the product engineering, primarily for the dynamic analysis add-ons. Okay. Before I show the next slide, I switch off my camera that you can see the full screen. You can ask questions via clicking that button with the question mark. Then you can enter your question here, press send, and then I will receive your questions and I will answer you. To the agenda today. Thomas will at first do a model analysis on that example here on the right side. In the next step, he will do a seismic design. He will use the results for the design of structural components. And he will also use the add-on building model to display story drift, masses per story, and forces in shear walls. Okay, that should be all from my side. I hand over the screen to Thomas. Thomas, it's your turn.
So, there we go. Thank you, Andreas, for the friendly introduction and a short summary on today's webinar. Also a half-full welcome from my side. And now we can just start with the program RFEM 6. And I'm going to guide you through the seismic design according to Eurocode 8. So you can see, already modeled building right here, as well as its loading. For the seismic design in general, the most practical approach would be to carry out the ultimate limit state without the consideration of earthquake forces first, like we imagine we've done this already for this building. And that means we have our model completed already, and we also have our loadings on that system. That helps a lot since the response spectrum analysis and the used modal analysis both depend on masses, and those masses are dependent on all the structure and all the surface loads, or in general all the loads in the system. The other alternative, which is also doable with RFEM 6, but I think not that often used, and it's also more, you could bring more mistakes into game if you just take the earthquake design from the beginning with you. So you would create your modal analysis from the start and pick a load case and so on. But that means you would have to reopen those dialogues more often. Means faster would be first model the structure and load the structure, and then we're gonna start with the earthquake design. And that's what we're gonna do here. We have our building already. We have a reinforced concrete 4-story building for industrial uses. We can see several walls which are always kind of needed for earthquake forces, at least for higher ones. They always help. We have some columns and we have slabs on each level. Let's go into one slab, for example, where I have a thickness of 24 centimeter. Also, we have a C2530 for all parts of the system. We also have a grounding plate right here of 80 centimeters. And this grounding plate is also completely supported. And yeah, that's gonna be an important part later on. So let's go over the loadings next. We do have the self-weight with additional self-weight defined. You can see the additional self-weight right here with 1.0 kilonewton per square meter on the roof floor and 1.5 on each other floor. The loads on the base plate are just simplified, also as the same as on each normal level. Also in the self-weight, we have the structural self-weight included, which can be activated in the load case. So that about our permanent loads. Then we can go to our live load at the roof. And there we have this 4 kilonewton per square meter on the top level. And we have our category A for the German Eurocode with 2 kilonewton per square meters on the other floors. And last but not least, we also have some snow loads, almost negligible, but we have them also included with 0.81 kilonewton per square meter. We didn't define any wind loads since today we will only investigate horizontal excitation due to earthquake and the seismic design. So now that we went through all our loading and all our system, we can go on and start the dynamic analysis. Therefore, we need to know RFEM 6. It has a base program where you can model your structure and apply the loading. Then we have several add-ons for those special analysis. And then we're gonna go here in this base data. This always also appears if you create a new model. So in this base data, we can go for the add-ons. And just as a hint, for me, it's best when I'm doing an earthquake design, I would just activate here our model analysis, our response spectrum analysis, our building model, and the corresponding design add-on, in this case, the concrete add-on. For our step-by-step show today, we will also apply those add-ons step by step. So let's start with the model analysis. And one special thing about the model analysis is that it's standard independent. Means we don't have to care about our standard here for the model analysis itself. So we can just apply the model analysis, and then we will see on this left-hand side that there is gonna be something added. And that's what we're gonna do. We press OK, and there it is, the model analysis settings. So we activated that add-on, and all the settings were included in our RFEM guided user interface. And with this, we could assume these model analysis settings, they are under load cases and combinations. Means I can go in here for the load cases and there we can initialize our modal analysis. Means creating a new load case of type modal analysis and then looking through all the options here. So let's start right away with our important masses only from load case or load combination. So within dynamic analysis, we also have the mass matrix in our system, in our calculation. Means we need to know what mass matrix will be there or what masses will appear in this mass matrix. And for the base knowledge of this matrix, we need to know a load case or a load combination, which we define here. And all the stuff inside this load case or load combination is then used for the masses in the modal analysis. We're gonna go for the combination while doing the response spectrum analysis in quite a bit. But right now I just want to go for the standard modal analysis. So here another thing, we can go into this modal analysis settings and there are some further options. First, let's go on the eigenvalue method and how many eigenvalues should be calculated. Here we can define either we use the user-defined method, so we just prescribe the number of modes that needs to be calculated, or we have more automatic approaches here. This is freshly new. For example, this automatic to reach the effective modal mass factors. And with this option, you can define what effective modal mass you want to reach. And then it automatically calculates enough eigenforms to reach this modal mass factor. Exactly. Maybe just one hint on this automatic algorithm. The Langzor solver cannot solve it that way. For this problem, we would need to take the root of the characteristic polynomial. So, but no worries, even if you did some, let's say, did pick the wrong one here, there will be a hint before you close this dialog. And also we have this automatic to find the maximum natural frequency. And that's kind of self-explanatory, so we can switch again. For today, or for this first example, we're gonna go with this user-defined method, and we're gonna pick out 4 eigenforms with the Langzor solver. The next thing is the mass matrix. So in this previous dialog right here, we selected which load case or load combination is used as the base for this mass matrix. But here we can also define if a mass matrix should have entries in each degree of mass freedom, kind of. So for today's example, I want to investigate earthquakes in X and Y direction. Means I won't care about the mass entries in Z direction. I won't care about the mass entries in X and in Y direction. I will keep with the Z rotation though, because you never know if there could be some torsional modes as well. And the next point would be the type of the matrix. On one hand, we have this consistent mass matrix, which is the most exact way, and but it also costs a bit of computational effort here. So the consistent matrix has even interactions between, let's say, the mass in X direction and the mass about the Y axis. That's like you could imagine it like with the stiffness matrix, there are some values K11, K12, K13, and so on. And with the consistent matrix, you would also have this in the mass matrix, means M11, M12, M13, and these places can also be filled in this way. On the other hand, we have the diagonal matrix. There this won't happen, so we won't have something like a M12 entry in this matrix. We have just a simplified diagonal mass matrix, and that's in most cases the way to go. So in general, I did use it quite a lot. And the last matrix, which is more for research purposes and shouldn't be used for any design purposes, is the unit matrix. That's like more if you want to understand some theoretical background of the stuff. So most engineers in the practice area won't use it anyway. So then we're through with this part of the options. We can switch the tab to this settings options on top. And there we can also define which loads should be treated as masses. In general, we have our gravity acceleration, which is roughly 10 meters per square second. And all the loads are just transformed with the help of this gravity acceleration to masses. And now we can decide, do we want only the set components of loads as masses, or do we also want to have full loads, so also the maybe horizontal loads, and they should be converted to masses? In my opinion, not that often useful in an earthquake design. Maybe in other dynamic procedures, but not for earthquake designs. And the most useful thing is here the Z components only in the direction of the gravity, because those are our masses, in my opinion, our really occurring masses. The next thing is we have here an option if you're gonna work with cables or membranes to use an initial strain to have less problems within the convergence, as well as having less problems with instabilities. And the last thing, which is really useful, and I will go after it a bit later again, is this neglect masses option. So there we can just freely neglect anything we want, surface masses, column masses, or whatever. Okay, so, but that's enough for the first thing. We could use also the well-known structure modification here, but what I wanna also say here is this option, this special option, consider initial state from. And this one can be used, well, it can be quite useful, since if we activate it, there will also be the geometrical stiffness matrix considered within the modal analysis. Means it calculates first this load case 1, and with the loads, let's say, for example, a beam gets a pressure force, and therefore its stiffness changes. And those changes are then taken over to the modal analysis with this option. It helps even further. Let's say, for example, you have a nonlinear diagram support. The base of the modal analysis is linear, so you can't consider nonlinearities in it. But if you use this initial state and you have like a diagram support, and in this initial state, we have one point in this diagram support, which is active and describes the stiffness of this support clearly. So we can also use this one point of the diagram for the modal analysis. And that's quite useful. And also just as a hint, it's not for Germany, since there's some exclamation for it in the national annex, but in the Eurocode in general, there will be considerations on the p-delta effects. And one simplified approach for it is to use the geometrical stiffness matrix. And that's just as an side information. So this p-delta, this simplified p-delta effects, would be considered by just activating this, consider the initial form. Okay, so now we have our modal analysis, we have everything set to go, and then we can go and calculate our modal analysis. So we have some load transfer surfaces, and the model means it always has to redistribute our some surface loads at first, and then it's just gonna start with our modal analysis, and it was quite fast. It was, I think, done in 10 seconds for modes. That's okay. And now we're ready to go and just look at our first mode. So let's see, we have here a displacement in the y direction. So I would say this is a dominant mode in the y direction. So I would assume the next mode to be dominant in the x direction. And so we see we have here, the displacement in the x direction. And the next ones, let's see, that looks like a torsional mode right here. So we have it here about the z-axis. So let's see, that's about the natural frequencies. We can also go into our effective modal masses. And there we go. We see here for the x direction, that was the second one. The y direction, it was the first one. We just have 40% of the mass participation in those directions. That's not enough, so we will go for that in a bit. And then I just wanted to know, okay, this third one is here, and we can see here this mass for about the z-axis. It's very high. That's why I know that's a torsional mode about the z-axis. So further, you can also see our participation factors on this next tab, as well as we can have the masses in the tables here. But new with RFEM 6, we also have the masses in the graphs. And so we have it defined in the x directions, in the y direction, and now we deactivate the z direction. So we won't have any masses in the z direction. Okay. Just maybe one last hint for the modal analysis. I mean, you have inserted here import masses only from node case and combination. What would also be possible, we can use additional mass. Means like in every load window, so we for nodal loads, for member loads, and so on, we can just select the load type mass and insert a mass here and just apply it to some node here. For example, this one, I applied it directly in our modal analysis, so it can be added there as well. And now we see them also with this bubble around. Okay, so that's already all for the modal analysis. Maybe one last point on it, and that's the scaling of the mode shapes. So when we go for the first mode, And let's see about the deformation. We can see here we have a scaling of the maximum absolute value of the deformation should be 1. And that's right here. That's the best, the best scaling method for visualization and quick understanding. But if you want to get behind the theory, you would look at this last one. And this one is from mass matrix. Means like the deformations are also scaled on the mass of the system. And you see here a lot of smaller values than 1. So we have 0.0025 approximately. And those values are used within the response spectrum analysis. Just as a hint, and that's how you can find those values. So in the next step, we're done with the modal analysis. I'm gonna just delete it out since now we're gonna go for our response spectrum analysis, and I wanna do it all at once right now. So yeah, we're gonna delete the results and we're gonna go into our add-ons. And inside the add-ons, we are gonna add our response spectrum analysis. And additionally, I'm gonna add our concrete design module. So with these 2 add-ons added, we should now take care on the use standards. And for this project, it's already presetted. So here on the bottom one, we find that dynamic analysis, and we already have our German national annex. If you need any older add-ons, you could press this filter button, and then you would see also the older standards implemented. Anyway, we will stick with our 2023-11 code and just use it for our analysis. So let's confirm it with OK. And then we also see we have here the static, this modal analysis settings from the modal analysis add-on. We have here now spectral analysis settings from this response spectrum analysis add-on. And we also have here added our dynamic loads, which include some response spectras or accelerometers. So we made the response spectras and our library of accelerometers available by just clicking this add-on. On the next step, we would go here. And now I will go over everything needed. So for the modal analysis, we need some base masses, which are used in the modal analysis. And in the different standards, they are defined how to combine our forces of the stories to get those masses. And with that said, we can choose here our classification and combination wizard. Also, I will activate here our sub-results, since I want to show you the results of each mode later on. And then we can go for our load cases directly. We can see here load case 1, 2, 3, 4. And depending on the standard, and there's some additional options for the mass combinations. So we can see we have here in both cases this class B. No, I think I said A early on. Never mind, I meant office areas and they're category B. So there are both category B, but the one is the roof load and the other one is the story load. And for masses, that can make a difference. So we have here this additional setting for our roof life load. we will take this mass combination option roofs, and for our story live load, we will take our mass combination option other floors. And when this is done, we have everything set up for the automatic process. So we go into our, let's say, magic tab, the design situations. And within those design situations, we will create a new seismic and mass combination. You can see it right here. We can also inspect the info button for the rule of combination here. And with this, it's already set up. We will use the standard combination wizard in this case. So it's gonna be second order analysis, load combinations. It's gonna be load combinations, They will be solved with the Newton-Raphson solver and so on. We can just say, okay, I'm fine with that, and go for this load combinations. And then we can see it just appeared. Like we didn't have to take any look in any standard for those combination factors whatsoever. We just have our finished seismic mass combination right here. And we can also see every factors if we want to see them. So it's done already, and we can go back into our load cases. The next step is to use the modal analysis. It means I'm going to create this new load case of type modal analysis. And now import masses, we will take our just created load combination right here. And that's the way to go. And in the next step, we can think about our modes. So earlier in the program, we needed to think through it ourselves and adjust this mode number. Maybe it wasn't enough afterwards, and we had to iteratively kind of adjust this number of modes. For today, we will just use this very big help, this automatic reaching of the effective modal mass factors. We're gonna pick this 90%, and we're gonna set the solver method to the root of the characteristic polynomial. This is done. We also use our diagonal mass matrix, since I think that will be enough for this model. And also, so we're done here and can go on for the settings. And this one can stay the same. I'm gonna include every set components of loads. Anyways, I have only set loads in the program anyways, so it wouldn't really change anything to select something differently here. But now this one is really important. We have a base plate in our system, and this base plate is 800 millimeters thick. Our other floors were 24 centimeters thick. Means like the base plate has an enormous contribution to our mass of the system. But now we have the problem that this base plate is completely supported. Means from my modal analysis understanding, if something is supported completely, then there won't be any mode that would activate those masses. So it would become impossible to reach those 90%. And that's where I'm gonna use this mass neglection for the base plate. So we're gonna go in this case for this user-defined one. We're gonna go for this neglect masses, and there we can just pick whatever we want to neglect masses of. We're gonna go for the surface. We're gonna pick this one by the object list and pick the base plate. If okay, it's just done. I'm just gonna ignore every mass of this base plate. And we will go for okay. We're gonna name it modal analysis. And then we are ready to go. We could also use now the initial state out of this seismic mass combination if we would want to consider some simplified p-delta effects, but like I said, we don't need it in this case, so gonna just leave it out here and create a new load case. And that's now we did the modal analysis. We looked over the modal analysis before as well, but now is the new part. We have here now, with the activation of the response spectrum add-on, also the response spectrum analysis type in our load case. And I will call it just in short RSA. There it is. And now we can go over everything inside it. First, we would have the option to consider accidental torsion as well. We can go for this 5% approach from the standard. Then we have our spectral analysis settings. Maybe first we import one modal analysis. In our case, it's quite easy. We just have one modal analysis. But if you would want to, you could even use more load cases for different modal analysis as well as different response spectrum analysis and compare them against each other. And you could also modify each with like structure modifications. So you could work in one model and just compare something against each other. Let's say it this way. So now we are here in this spectral analysis, and we can also look at our spectral analysis settings. And there it is. It's mainly about our combinations and how results are saved and so on. So at first, we're gonna use the X and the Y direction. And for each direction, well, let's say we have a mode, and for each mode, we have a bit of mass contribution to one direction. So what we need to do is for each direction, so for example, for the X direction, we need to combine each modes with each other. Now, the thing is with those modes, they could be like in a different direction. They could like strike each other out in some places. And that's where we need to do quadratic combinations. With this one, we have the SRSS rule, which means all the results of each mode are squared. Then they are all added together. And after that, the root is drawn for this complete result. And that's what we get here. The CQC, the complete quadratic combination, would be also for the consideration of damping, as well as for the consideration if modes are next to each other. In the Eurocode, I think it was about 10%. So if mode 1 or mode 2 are less than 10% away from each other, then we would need to use this CQC rule. If possible, always use the SRSS rule because it's more, it just delivers better results for design. And the absolute sum, it's self-explanatory, but never used, in my opinion. So we won't do that. We're gonna go for the SRSS rule. And then we have to decide within those combinations, within those quadratic combinations, the sign will be lost. So we always have an envelope result of plus results and negative results. Also, the connection between some internal forces are not given anymore. For example, if you have an moment about the y-axis. And when this exact moment appears, we have also a shear force in z direction. And in general, those two internal forces are linked to each other. So the problem is with the standard SRSS rule, we also lose this information. That means we would design always for the maximum moment and the maximum shear force, even though they maybe don't occur at the same time. And that's where we stepped in and introduced this equivalent linear combination. So this is, let's say, state of the technical art in our opinion, since it just links again our moment with its shear force. So we don't have to design every time for the maximum value with the maximum value of another internal force, but we have the linked ones and therefore more cost-effective design. So we're gonna use that as well. And what I'm also gonna do is we're gonna save the results of all selected modes. That's just for making them inspectable later on, and I'm gonna show you some single mode results as well. Exactly. Then the next point would be the combination for the different directions. So in this case, we will have the x direction and the y direction. So we can go here. We could use the squared root sum. We could use the SRSS rule as well. But we also have in the Eurocode 8 something that's called the scaled sum combination. And there we can define, per default, it's like mentioned in the Eurocode, 100% in one direction and 30% in the other direction. That's something we can use here as well. And if you have like a special project, it could be useful to change it to 40% or something. But that's dependent on the project and on the standard used. So we will go with this scale sum 130 and click OK. So we have this first tab done already. And we can go for our response spectrum. There we go. We're gonna go for the X and the Y direction. The same response spectrum is already used for both. And now let's see in our options how to get those response spectrums. Let's start with the simply user-defined one. Maybe just as a hint, if you have something from these other options and you switch to user-defined, it will also be switched to a table spectrum kind of, and you can also like im and export all those values as you like. So the user-defined kind of just easy. The same one with the G factor, which just means that the accelerations are inserted in dependency of the G factor. Then the next point would be to generate one response spectrum from accelerograms. We could also choose our damping value here, our direction, and so on. And we could take a use from our well-filled library here. Just gonna show you this one. Right here, you see lots of different countries in this case. Let's go for that's just an example of some ground measurements of an earthquake in Auckland Islands in New Zealand. And this information can be used to produce a synthetic response spectrum. So let's go back. We're not gonna use the accelerogram for this project. What we're gonna do, and that's the most used one, is we're going to use just the response spectrum according to the standard. In this case, the Eurocode 8 with the German annex. So yes, we need a design spectrum. We need to pick a behavior factor. We're going to use the 1.5. I think it's limited to 1.5 in the German annex. And then we need to have some more values inserted here. So the 3 values we need here, the rest is automated, is the ground type, the importance class, and our reference peak ground acceleration. For the importance class, it's project dependent. We will pick 2. The Q factor, we set it to 1.5. And then we only need the ground type and the AGR value. And for this, we will go shortly for our web service tool. So this is the Dlubal homepage. And within this homepage, we can go for our online services, and there the seismic load maps. We directly switch, okay, United Kingdom, that's not what I want. I want to go for the German one and the seismic one. And then we see we have the 475 years reappearance period. So that's what we take here. And then I did want to go for something in Ingolstadt, but I think, let's see, 0.7. Now I want some, let's say, the biggest earthquake in Germany, kind of. So we're just gonna take this one right here. Maybe you can see the map of Germany again. I think here next to Frankfurt, next to Koblenz, we have also old volcano. That means that has some relations with this earthquake map, just as a side information. But for this one, we will go for the most drastic one, which, right here. Let's go into Elbingen. There are some sheets. We're gonna create a new one right here. And okay, now it's selected. Now we can take our AGR value, 1.458, back to the program. 1.458, and we can also change this one here to the subsoil class, depending on the standard what is needed here. But there we see we have a subsoil class of R. Means we can go here for our subsoil class. R is already picked. The A, B, and C is dependent on the direct ground under the building, so that is gonna be given within the geotechnical report, and we just assume it to be B. So what changes with the subsoil type is mainly those corner points, as well as this multiplication factor of this peak acceleration on top of the response spectrum. Okay, so BR, we are ready to go. We have our spectrum now completely defined. We could also just scale it right here if you want to do that on whatever reason. And the next thing would be to select the modes. Now we could calculate it right here and see everything. But I'm going to just start and calculate all in this case. And then we're going to see something right in a second. Okay, I didn't care about the concrete design yet, so I'm just gonna go over it. And there we see we have now our response spectrum analysis right here, this load case 6, and it is made out of several load cases. And in a second you will see they will be almost done at the same time. Means we have here a new solver mechanic where different load cases can be distributed onto different processor cores. And that's something we're just going to use here. And yeah, let's see, I think model is through with 30 seconds. And also our spectral analysis is through. We can go here. And yeah, we already have the result. Perfect. I'm gonna just go for this one here. Let's go into our spectral analysis, and then we can have like, let's see, the overall result first. And yeah, let's start with this combination and how it worked. So as you can see, we have here in X, in mode shape 1, we have this deformation, as well as for this mode shape 2, we got also this X deformation. So it is nothing else than the mode shape 1 was used, and all the masses were like accelerated in X direction. Next step, mode shape 2 was taken, and the masses were accelerated in X direction again. And now this X total, that's nothing else than the results X mode shape 1 squared plus X mode shape 2 squared, and so on. And in the end, the root is drawn out of the sum of those modes. That's how this X appears here. For this one, we have the 130 rule in both options. So we have one time 100% is X direction plus 30% of the Y direction, and vice versa. And the scale sums is nothing else than an envelope over those two top results. That means we have the worst results are just in our scale sum envelope. And that also means if we have enough mass participation, we just don't need to care about this bottom one anymore. We just use the scale sums envelope, and the rest, well, we don't really need it. So maybe just one hint. You could, of course, use it to understand the modal analysis and the response spectrum analysis. That's like the main reason for it. But okay, let's go for the scale sum envelope. We also have here like our results for each member as well as for each surface and node. That's well known in, I think, every static analysis, static analysis as well. Just nothing big changed here. Just one more thing. If we go, for example, the normal forces Vy, and we see right here, let's go for the wired model. Exactly. And we have here our result in this case. Now, on our next step would be to use it in the design for our, concrete design. But okay, I just found another thing which I wanted to show you. We stay at the results for the internal forces, and we have here plus and minus. So that's what I meant with we would lose our signs of the internal forces. but they're both taken into account in the design. So that's quite well. And now we can go for the design. And that's something that was also enhanced with this design situations. We can just go for a new design situations of the type, in this case, ultimate limit state seismic. We're gonna also say it should be used for the concrete design. And now there's something important. We're gonna use the combination wizard again, but we can't use this load combinations wizard because we have an envelope of results and we can only combine them with other results. That means we need to create a new load combination rule here and just set it to result combinations. We can ignore the rest and go for it with the OK. Then we also gonna activate it for the concrete design and select this result combination wizard here. And then it's done. And now we can go into our result combinations and we see our result combination is created right here. We can go for this assignment and we can see now we have all our loads included as well as our scaled sum of the envelope result of the response spectrum analysis. So we could change it here, even though in my opinion that doesn't really make practical sense. It's more for testing reasons. And yes, so we're gonna stick with the scaled sums envelope and that's it, that's done. We have the result combination here already. We can click OK. And yeah, then I would say we can just calculate everything again. So let's see. Okay. Now I think it was about 30 seconds here and about 1 or 2 seconds in the modes. There it goes. So the concrete design. Well, I think there should be a warning again, but let's see. Oh, it worked out. And now we can go just for the concrete design. Let's see what I did there. I should have gone with the input data. Exactly, we have here the objects to design, just everything. Okay, it's a bit more than I wanted, but we can just go for only the results I wanted anyway. Let's go here. We're gonna take, for example, this member, and we will have, in this case, the shear resistance on this top side. So what we use, what is used in this concrete add-on is also shown here. We have the result combination 1 in this case, which is our earthquake combination. It delivers a 30% ratio, and we can also investigate the whole design check right here as in every other mode add-on as well. And we can also check the internal forces here for the design check and everything that's needed. So that's done here already. And since we are running a bit short of time, that's all for it here. Maybe just one more thing I wanted to show you, and that's in our base options in the add-ons, our building model. We're gonna activate it, and then it's gonna be in our data navigator right here on the left side. We're gonna pick our building model, and it's really simple to use. We can just go here. In my case, I do know that we have an elevation of 3.35 meters here, and the elevation is the same for each story. So for this simple case, I can just go 3 times on this new story button, and it's done. One more thing, we could change here our floor modeling to rigid diaphragm, load transfer only, and soon to come semi-rigid diaphragms. But for today, we will just leave it as it is. And yeah, it's done already, and that's it. So we just got our results in here. And now we will go into this, let's say static analysis, for example. We can go into our self-weight loss case, and there we have now our results by stories. This holds also for our spectral analysis. The same here. We can go for the spectral analysis and also look at our results by stories. Means we have our location of our resultant of the forces. We also have interstory drifts for some serviceability checks. We have centers of mass and rigidity. And we have the sensitivity coefficient, which is used sometimes, or let's say it is defined in the Eurocode 8 and neglected in the German annex, but nevertheless, you can use this one to find out if your system needs to include p-delta effects or not. Okay, so that's it for this one. Maybe one last thing which also could be used is we also have shear walls. Let's pick one example. I'm gonna pick this one as an exemplic shear wall here. The shear walls would need to be defined in this case. So I'm gonna go here and just go for this whole wall from the bottom to the top. We will also generate a result section. And we need to calculate it one more time. Now it's done, and we can just go for it and calculate it. And maybe in the meanwhile, also the printout report. Within the printout report, you could include either the modal analysis results, so the modal participation factors or the eigenfrequencies, but most likely you would just include the response spectrum analysis results, because there also the used natural frequencies are given. And you can also put out every result we just saw in the tables. No, there's nothing kind of new to it, new to the usage of the printout report. You can just put in whatever you like from the modal analysis as well as from the response spectrum analysis and the building model. So now we're here. And we see we are in the load case number 6. We also see our automatically generated, this case, result section of this, of this shear wall, and Exactly, we need to go into the results by stories, and there it is. Now we also have our forces in the member shear walls as well as our member forces in shear walls. So the member forces in shear walls is just that this is an imaginary beam of the same dimensions. So exactly, and yeah, that's how you can investigate the seismic design within RFEM 6, and also go on some detailing with those shear walls and how to get the results by story. I hope you enjoyed this webinar, and I think that's all from my side. So thank you a lot for listening, and Andreas, you could take over again now.
Okay, Thomas, thank you for your nice presentation. An additional hint from my side, you can book your free online appointment, such as a product demonstration for our main programs, RFEM, RSTAB, our wind, our section, and so on, or to the add-ons. Just contact our sales team via that link here, or you can also scan the QR code. Okay, then it should be also all from my side. I thank you for your attention. I thank Thomas for his presentation. Yeah, I hope we meet each other in a future webinar. Yeah, until then, bye-bye.